Start the recording. Welcome everybody to our second seminar on asymptotically safe gravity. We are very happy that Marc Schiffer from the Perimeter Institute is here today with us. His general interest is probing quantum gravity, and on this topic he finished his PhD in Heidelberg last year in the group of Astrid Eichhorn. More specifically, he worked on phenomenological consistency tests of asymptotically safe quantum gravity and matter, which is also going to be the topic of today's talk. So welcome, it's very nice to have you here. And without further ado, the floor is yours.
Okay, thank you very much for the nice introduction, and thank you also for the invitation to give a talk in this, I think, very nice seminar series. So as Katharina said, I will be talking about phenomenological consistency tests of asymptotically safe quantum gravity and matter, which was part of my PhD work that I only finished last year. And we already had last month the talk by Raphael, so I will rely on that a little bit in the concepts that he has introduced, because I think he did a very good job in introducing asymptotic safety and some of the machinery. So just to remind ourselves what asymptotic safety actually is about, and before I actually do that, let me just emphasize that please ask questions if there's something unclear, if I'm too fast, or if I say anything that you don't understand or don't agree with. Just speak up, and I'm happy to try to answer your question. So let's dive in. And so when I think about quantum gravity, I think about taking a patch of space-time and then zooming into that patch of space-time. And at some point I will see like small quantum fluctuations to start appearing. And if I zoom in further, these quantum fluctuations might grow. And in a perturbative setup, at some point, I would not know what happens if I zoom in further, because I lose predictivity, because I have to add more and more and more free parameters to describe my theory. Now, the key idea of asymptotic safety is that when zooming in after some certain scale, roughly at the Planck scale, that if I zoom further in, nothing changes anymore. So the quantum fluctuations, my patch of space-time will just look the same after I zoomed in, and after I zoomed further in. So, and this is the key idea, namely the quantum realization of scale symmetry. So I zoom in, but the picture with my space-time doesn't change any further. And in terms of couplings, of scale-dependent couplings, which is the language that I will be mostly using in this talk, this just means that at some certain scale, k, the coupling becomes constant, and this realization of scale symmetry is actually nothing unfamiliar to us. It also happens, for example, in QCD, where asymptotic freedom is realized, where the UV kind of realizes or restores some kind of classical scale invariance. And the difference in asymptotic safety is that this scale invariant regime happens at a non-vanishing value of G, so of a dimensionless version of the Newton coupling. And here I'm just showing you like two sample beta functions for asymptotic freedom and for asymptotic safety. And here we see that asymptotic safety can arise as a balancing between a dimensional contribution, here this epsilon, and quantum fluctuations. And the key, or the important bit of this quantum realization of scale symmetry is that scale symmetry, as any other symmetry, imposes conditions on the theory. And in the case of asymptotic safety, scale symmetry imposes infinitely many conditions on the couplings of the theory space. And therefore, one can realize a predictive quantum, or one would realize predictive quantum field theory of the metric. And as I said, so asymptotic safety as a concept, in the sense of a quantum realization of scale invariance, is not unique to gravity. but it can also be seen in Gauge-Yukawa systems where actually the fixed point is under or can be under perturbative control, and then in Gauss-Neuville and the Wilson-Fisher fixed point and so on also can realize asymptotic safety. So this is like the physical scenario that I'm thinking about. So the quantum realization of scale symmetry. And then in gravity, there's several tools that can be used to explore asymptotic safety. And there's, of course, perturbative methods that then get extrapolated or resummed in terms of some epsilon expansion, typically about 2 dimensions. Then one can use lattice methods, namely dynamical triangulation, or specifically Euclidean or more commonly causal dynamical triangulations. And here I cite the original papers and also a recent review by Renormalization. And finally, there's the functional renormalization group, where also here I cite a recent review of possible applications of the FRG. And in this talk, I will mostly focus about functional renormalization group methods. But in the last bit of the talk, if I have time enough, I will also try to highlight how, or one evidence, or in my opinion, evidence that also lattice methods, in particular Euclidean dynamical triangulation, can help us to detect or to find asymptotic safety in gravity. So let me first start with the FRG bit, and again, so this is the main tool, and again, Raphael last month already talked quite a bit about it, so I will be a little bit briefer. So the key ingredient of the functional renormalization group is the so-called non-perturbative renormalization group equation, and the key ingredient here is this gamma k, which is a scale-dependent effective action. Think about it as some effective action that contains all operators that are compatible with the symmetries of your system. And you can, and this gamma k, where k is the scale at which we probe theory, or up to which quantum fluctuations are integrated out. And this interpolates between the classical action when no quantum fluctuations are integrated out and the full quantum 1pi effective action when all quantum fluctuations are integrated out. And this RK is an infrared regulator, and it implements kind of a Wilsonian idea of integrating out quantum fluctuations according to their momentum share. And we can extract beta functions, so the scale dependent of couplings, out of this flow equation by projecting on these specific tensor structures and momentum configurations. However, one disadvantage is that since gamma k contains all possible operators that are compatible with the symmetries, in practice one needs to truncate this gamma k in order to be able to do any practical computations. And under these truncations, this flow equation is not closed anymore, and we introduce some systematic uncertainties in our computations. And the second challenge or drawback of this method is that a priori it's formulated in Euclidean spaces because we need a notion of momentum to perform this momentum share-wise integration, or I mean to be able to distinguish whether a mode is UV or IR based on the momentum. And so in principle it's Euclidean, but recently there has been quite some effort to try to continue or to formulate also a Lorentzian version of this flow equation. So there is some progress into trying to also address or to use similar methods also in Lorentzian spacetimes. So now with the key physics idea and also the method in mind, the point we can go ahead and compute quantum gravity, but one main difficulty in any approach to quantum gravity is but the typical scales at which quantum gravitational effects become relevant are extremely high. And therefore, it's very difficult to gain direct experimental access to the fundamental properties of our universe. And therefore, more commonly, only consistency tests are possible. And these can be like internal or theoretical consistency tests, or also phenomenological. And one key, one I think very nice example of some mathematical consistency tests is in string theory, where just by demanding mathematical consistency, d equals to 10 turns out to be the dimensionality that a string lives in. And any other dimension would be ruled out by mathematical consistency in that case. And so I will take the point of view that in our universe, there's also a lot of matter. And just the observation of matter or of specific types of matter provides a broad range of observational or phenomenological consistency tests, in the sense of, okay, there are a lot of fermions, so actually our theory of quantum gravity, if it was to describe our universe, also should be able to be compatible or to accommodate these number of fermions. So why I focus on the gravity-matter interplay is that actually we know a lot of things about matter, and we can test our theory for consistency with the existence of matter. But I will, in this talk, go a little step further and say, so can actually, beyond any consistency, can the interplay of gravity and matter also put constraints on some fundamental properties of our universe? For example, that, well, if we want to have light fermions in the infrared, then there must be more than a certain number of fermions. Or if we want to observe a UV complete abelian, or if we want to have a UV complete abelian gauge sector, then our dimensionality cannot, the dimensionality of our universe cannot exceed a certain number. And these are actually some of the motivational questions that I will try to address in the following. So really just understand it as big questions, and what I will provide you are just merely like first steps or ideas on how we could actually try to answer these kind of questions. And these are like, why do we live in 4 dimensions? So what singles out 4 dimensions? Why are there so many fermions, or in particular, why is there more than one generation of fermions? And whether or not Lorentz invariance is a fundamental symmetry. And again, so these will be 3 parts of the following discussion. And keep in mind that all of these, or all the first steps that I provide towards answering these questions are performed within toy models and approximations. But nevertheless, I think they highlight how powerful the interplay of quantum gravity and matter might actually be. So let's start with the first motivational question. So why do we actually live in 4 dimensions? And for this, let's focus on the U1 sector of the standard model. So let's focus on the abelian gauge sector. And there, quantum fluctuations turn the vacuum into a screening medium. And this is already encoded in the one loop beta function, which I denote here. And the crucial bit is that the leading order coefficient is positive, which means that the Gaussian fixed point is is infrared attractive, which means that if I start close to this fixed point, that if I now think about going to higher energies, so if I go to higher energies, that I will be pushed away from this fixed point. And the arrow indicates the flow towards the infrared. And this, so the positive sign and this screening nature of the vacuum results in the Landau pole, which already appears at one loop perturbation theory, and which indicates that the theory breaks down at a finite scale. So if I just started with some non-vanishing value of the gauge coupling at some scale, then sooner or later, so at some scale, my coupling, at a finite scale, my coupling would diverge. And this indicates the breakdown of the theory. And actually, there are indications from lattice simulations and also from functional methods that this Landau pole actually persists beyond perturbation theory. And the presence of such a Landau pole, so of such a divergence, indicates that a UV completion of that sector requires some new physics. And of course, I mean, in quantum gravity, we would say one natural, or when thinking about quantum gravity, we would say one natural candidate of such new physics would be the inclusion of quantized gravity into this picture. And this is exactly what I will try to advocate. So if we now include, for example, asymptotically safe quantum gravity, then gravitational contributions or gravitational fluctuations contribute to the scale dependence of the Abelian hypercharge of the U1 gauge coupling in such way that are shown here, which is linear in the coupling itself. And now, if Fg was positive, then the gravitational contribution would be anti-screening, and this would mean that the free fixed point here becomes actually infrared repulsive, so it becomes a relevant direction of in theory space, which means that the gauge coupling can become asymptotically free, so similar to the non-Abelian gauge coupling. And actually, FRG studies indeed indicate that a positive FG is possible in 4 dimensions, and there's quite some indications for that. And also there's a recent work by Gustavo De Brito, who's going to give a talk I think next time in the seminar series, and Astrid Eichhorn, where they very carefully study the scheme dependence of such a gravitational contribution to the metacoupling, or to the Abelian hypercharge. And so let's assume now that Fg actually is positive. Then, as I said, the Gaussian fixed point for the Abelian hypercharge becomes infrared repulsive, and therefore the coupling is relevant, and we can have a UV completion where at very high energies the Abelian gauge coupling approaches 0. So we have a free fixed point for the Abelian gauge coupling, and then quantum fluctuations drive the coupling towards an interacting value at lower scales, and then at the Planck scale, quantum fluctuations of the or gravitational fluctuations turn dynamically off, and the flow continues towards the value of the standard model, or towards like just the standard model flow. And additionally, if Fg is positive, you can see here that there's a second interacting fixed point for the Abelian hypercharge, and at this fixed point, the hypercharge actually corresponds to an irrelevant direction. And an irrelevant direction means that the coupling or the infrared value of that coupling becomes a prediction of the theory. And we can kind of see that here. So all these blue trajectories are the trajectories that emanate from the Gaussian, the non-interacting fixed point of the Abelian hypercharge. And then there's trajectories that are not UV complete, so that are UV unsafe. And these two regimes are separated by one particular predictive trajectory that emanates from this interacting fixed point of the hypercharge. And then really along, when the entire trajectory is confined along this, along a predicted given predicted value, and the infrared value of coming from that fixed point can be computed and predicted. And this predictive scenario has been investigated by Fleur Festieren together with Astrid Eichhorn. And so in summary, in d equals to 4, there are indications that metric fluctuations actually might induce a UV completion of the standard model matter sector, in particular the abelian gauge sector of the standard model. And additionally, this UV completion might actually be predictive in the sense that if this interacting fixed point would be realized, a coupling that is a free parameter in the standard model would be a prediction from the interplay from our theory of quantum gravity and matter. Now, so this was all talking about d equals to 4. So what happens if we now go to larger dimensions? And the main difference is that in higher dimensions, the abelian gauge coupling is no longer dimensionless, but it becomes dimension-full. And this dimensional contribution adds an additional, or this dimensionality adds an additional contribution to the scale dependence of the gauge coupling. And we see that now this gravitational contribution competes directly with the term coming from the canonical mass dimension. And in order to provide a UV completion for the gauge sector, so in order to turn the free fixed point into a relevant direction in theory space, this Fg has to grow larger and larger and actually has to overcome a critical value. And this can be achieved by increasing the value of the gravitational coupling. So by going to higher values of the Newton coupling, for example, we can make this gravitational contribution larger. And at some point, we would overcome the dimensional term, but this requires that the UV completion of the abelian gauge sector kind of shifts into a more strongly coupled regime, in the sense that we need higher values of the gravitational or larger values of the gravitational interaction in order to render the abelian gauge sector UV complete in the larger than form. Now, so this is one ingredient. So we need, or when going to larger dimensions, we need more and more strongly coupled gravitational theories. Now, specifically in asymptotically safe quantum gravity, there are several indications that metric fluctuations can actually not be too strong. And the reason is, and Raphael also already has mentioned this a little bit, is that the interacting nature of gravity percolates into the matter sector and induces new interactions in the matter sector. And in these new interactions, beyond the weak gravity regime, metric fluctuations could actually, or can actually, induce new divergences in these interactions. And I will illustrate this for one example, for the abelian gauge sector. So just let's take an abelian gauge field with a field strength tensor. Then if we start just with a standard kinetic term, and we now think about expanding this in metric fluctuations and computing diagrams like radiative corrections coming from gravity, then we can produce from this kinetic term a 2-graviton, 2-photon vertex that can be combined to such a diagram by a metric loop from metric fluctuations. And we see here that this diagram contributes to a 4-gauge field interaction, so to something like an f to the 4 interaction, but it's independent of this interaction itself. And we call this that this interaction is induced. And the reason is that schematically we can write the beta function of this interaction W2 in such a form where the crucial bit is this term, is the presence of this term B0, which is independent of the coupling itself. And this means that, so if B0 is non-vanishing, and it actually is non-vanishing if gravity is turned off, if gravity is turned on, sorry, then W2 equals 0 is not a fixed point anymore. And so for G equals 0, this term vanishes because there's no graviton loops, and therefore this kind of diagrams disappears or just vanishes. So we just have in a sense, a parabola in this approximation, and we have a Gaussian fixed point at W2 equals, or we have a fixed point at W2 equals 0. Now, turning on gravity, B0 will be non-vanishing, and therefore W2 equals 0 is not a fixed point anymore, but instead the fixed point shifts towards an interacting fixed point. And this is what we call that this coupling is induced, because we can't set it to 0 consistently. And now in such an approximation, it can actually happen that if we turn on gravity further, or if we increase gravity further and further, that at some point we push this kind of parabola so far up that the fixed point collides with an additional interacting fixed point and vanishes into the complex plane. And in this scenario, so this red dotted line here, there's no fixed point in this induced interaction anymore, and this coupling wouldn't be UV complete. And therefore, so the fixed point only exists for a certain bound on the value of B0, which can indeed be turned into a bound on the value of the Newton coupling of our gravitational parameters. And this is what we call the weak gravity bound, because it constrains the gravitational interaction to be in the near perturbative or not too strongly coupled regime. So this is the second ingredient, namely that at least in these in the systems that we have currently looked at, there are indications that metric fluctuations must not be too strong. And I would also like to mention that we are currently in the process of studying the weak gravity bound. So trying to answer the question whether there is actually this constraint by going beyond polynomial expansions of the action and considering a function of the kinetic of these f squared operator, for example. But here, let's just assume, or let's just continue with the observation that for the Abelian gauge systems studied so far, there is a bound on the strength of gravity. Now, let's combine this with our previous observation, and we can then evaluate this gravitational contribution Fg and the weak gravity bound together. So these will be FG computations, and study explicitly the condition that Fg is large enough while still remaining in the weak gravity regime. And in d equals to 4, we see, so in green, I indicate where Fg is sufficiently large, so where Fg is positive, and in red, I indicate the regime which is excluded by the weak gravity bound. And we see that in d equals to 4, there's actually a large region in the gravitational parameter space spanned by G, which is the dimensionless version of the Newton coupling, and lambda, which is the dimensionless version of the cosmological constant, where a UV complete gravity matter system might be possible. Now, the situation changes in d equals to 6, where the entire region where Fg is sufficiently large is located in a regime that is excluded because of the presence of a weak gravity bound. And therefore, indeed, this indicates that requiring a UV complete matter sector actually can put constraints on the gravitational fixed point value, so on the dynamics of gravity, but it can also constrain fundamental properties of our universe, for example, the dimensionality, because in, for example, d equals or larger than 6, at least in our approximations, we don't find indications that a UV complete Abelian gauge sector is actually possible. So in a sense, why do we live in 4 dimensions? Because maybe it's not possible to accommodate a UV complete Abelian gauge sector in d equals to 6 or beyond. So that kind of might single out 4 or 5 dimensions. Now, I think I have to speed up a little bit, but let's dive in with the second question. So why is there more than one generation of fermions? And so here, just as a reminder from the previous bit, that there is indications for a predictive UV completion of the Abelian gauge sector, where the fixed point value actually is proportional to Fg and the number of fermions in the system. And now let's focus on a similar set of induced interaction as before, but instead of gauge fields, let's focus on fermionic interactions. And there's these like lambda plus minus. So these are for like two chirally symmetric four-fermion interactions, and therefore we expect those interactions to be induced. And they're actually also induced by just the gauge interaction. And these four-fermion interactions are typically also studied in the context of QCD. And very similar to what happened before, these interactions are induced. And now turning on this external coupling, which can be either gravity or some other external coupling. For example, in an Abelian gauge coupling, the same picture happens or the same picture can happen as before, namely that if all external fields are 0, then we can consistently set these couplings to 0. If we turn on some external field, let's think about an Abelian gauge coupling, then these two interactions will be necessarily non-vanishing. And if we make this external interaction too strong, it can happen that we produce a fixed point collision and our system, so these chirally symmetric induced interactions, wouldn't be UV complete anymore. And in analogy to QCD, where a too strong gauge coupling leads to the divergence of these higher order induced fermionic interactions, we investigate that in the context of gravity. And in QCD, the divergence in these four-fermion interactions is actually used to detect the breaking of chirosymmetry and the generation of fermion of the formation of fermionic bound states of protons and so on. So in the gauge gravity fermion system, we can now map regions of broken and intact chirosymmetry. And this is shown here in the plot, where again, we showed in a two-dimensional parameter space spanned by the dimensionless version of the Newton coupling and the cosmological constant. And these different lines indicate the, in a sense, excluded region. So the analogous or the analogy of the weak gravity bound that I mentioned before. But here, this exclusion actually comes from strong from a strong gauge coupling, which again is triggered by gravity. So for nf equals to 2, so 2 fermions, this gray region here would be excluded by demanding that a chirally symmetric theory space is UV complete. And now the second ingredient is the fixed point value of the gauge gravity fermion system, which is located for nf equals to 2 here. So it's actually located in the region where the would-be fixed point, where there is no fixed point in the matter sector. And now for nf equals to 3, this excluded regime, so this regime where chirosymmetry with broken shifts, and also the fixed point value shifts. And we see that for nf equals to 3, actually the fixed point value lies in the regime where chirosymmetry breaking is avoided. And this continues to be so when increasing the number of fermions. But this in turn means that actually the interplay of quantum gravity with gauge fields and fermions might give rise to a lower bound on the number of fermions, because in our computations, for example, for nf equals to 2, so just 2 fermions, the chirally symmetric theory space is just not UV complete. And now let me come to the last point. So whether Lorentz invariance is a fundamental symmetry. And for this, we take as an approximation for the dynamics of gravity and matter, we just take the Einstein-Hilbert action. So just curvature, so just the Newton coupling and the cosmological constant for gravity, and again an Abelian gauge coupling, so Lorentz invariant Abelian gauge coupling. Now we split our metric into a time like a normalized vector and an orthogonal space like metric. So we kind of foliate our space-time into a vector and a metric and a spatial metric. And with this access to the foliation structure, we can actually single out a preferred frame by breaking Lorentz invariance in the gravitational sector, parameterized by gravitational lift couplings AI. And now the idea is to study the effect of a preferred frame on the matter sector in the sense of on an Abelian gauge coupling. And we do that by studying the scale dependence of such a Lorentz invariance breaking Abelian gauge interaction. And here this K can be, or is Lorentz invariance violating if it also depends on n, for example, explicitly. So if it depends on the preferred frame. And again, we can extract the scale dependence of this lift coupling psi or zeta. And schematically, it has a similar form as we have seen before. And crucially, there is a zeta independent contribution, which is a function of the lift gravity couplings. And it's non-vanishing in the presence of gravitational lift couplings. So just the same mechanism as before. And again, so in the presence of gravitational lift couplings, zeta equals 0 is not a fixed point. And therefore, if we set zeta to 0 at some scale, then when flowing towards lower scales, a non-vanishing value of this Lorentz invariance violating meta coupling will automatically be generated. So we can't, so in the presence of gravitational lift couplings, we can't avoid also having a Lorentz invariance violating meta coupling. And this actually means that Lorentz invariance violations percolate into the meta sector. And now the idea is that let's assume we have some UV completion where some initial conditions, or where an initial condition for our coupling zeta is set, then there is a infrared attractive fixed point for this coupling zeta, and this will be approached when flowing towards lower energies, and will be approximately realized around the Planck scale. Now, the fixed point value itself is a function of these gravitational lift couplings, and we can shift it around by shifting the value of the gravitational lift couplings. At the Planck scale, quantum fluctuations of the metric turn off, and we just flow down towards the infrared, towards the standard model, where we can actually perform experiments. Now, by constraining psi or zeta, at very low energies with experiments, we therefore indirectly also constrain the value of zeta at the Planck scale. And this value of zeta at the Planck scale again is given, or is determined, at least approximately, by the gravitational lift couplings. And in that sense, we can put indirect constraints on the gravitational lift couplings by just computing the effect of gravitational lift couplings on the meta sector and very, very carefully measuring or constraining lift couplings in the meta sector. And just to illustrate how strong these indirect constraints can be, and it's here, so take it with a grain of salt, it's all a toy model. We can combine them with the direct bounds from gravitational waves and cosmological observations, which is indicated here. And this is just one cut through this three-dimensional plane. And if zeta in the infrared was constrained to be smaller than, for example, 10 to the minus 40, all this additional region here, so everything here, would be excluded by the non-observation of Lorentz invariance violations in the meta sector. And of course, the weaker, in a sense, the constraints in the matter sector become, the weaker also these indirect constraints on the gravitational diff couplings become. So the key point here is that the interplay of quantum gravity and matter might actually pose additional indirect constraints on Lorentz invariance violations in gravity. And yeah, so this concludes the part on the functional renormalization group point. And so do I have 5 more minutes? Yes, okay, yeah, thank you very much. And now let's briefly shift completely. Let's switch gear and as I announced before, think about asymptotic safety from lattice computations. And I just want to highlight this because in my opinion, I mean, as I said several times, like any method that we use always has systematics and uncertainties. We have to perform approximations at some point or another. And therefore having different methods with complementary systematic uncertainties is actually very crucial and very, very powerful to investigate actually the physical scenario and to try to extract the physics of a system independent on the method that we use. And therefore, I just highlight that one might or hopefully can also use lattice methods to investigate asymptotic safety. And the idea is literally that we take space-time and discretize it in terms of triangulations. So we have our sphere, we discretize it in triangulations, and then we eventually want to recover continuum space-time, and therefore we make our triangles smaller and smaller and smaller. And when making this smaller, we then eventually will be looking at, or we will be looking for continuous phase transitions, and asymptotic safety on the lattice would be realized if a higher order phase transition exists. And in this discretization of space-time, one would replace the path integral over the metric by a sum over different ways on how we can glue all these triangles together to get our nice sphere out. And these gluings, or these ways on how to glue our space-time, is then weighted by the Euclidean Einstein-Regge action. And just very briefly, how can we actually get this this discretized version of the Einstein-Hilbert action? So the volume term is kind of simple because it's just a volume. So we just add the volume of our different four simplices, or four-dimensional triangles, quote unquote. And for the curvature, it's very intuitive to think about a two-dimensional picture and to triangulate it. And so then if we look at this vertex here, for example, we see, okay, 1, 2, 3, 4, 5, 6 triangles meet here, and the so-called deficit angle is 0. So 2 pi minus the angles that meet at this vertex is 0. Now, if we cut out one of these triangles and now tried to glue these two blue lines together, I mean, just take, you can literally do this with a piece of paper and cut out a piece and try to glue it together, and you will see that you have to add curvature to your paper. And this is how one can define, or how one can define curvature on a lattice, namely by computing the deficit angle at a vertex. And this is in 2 dimensions. And now upgrading that to 4 dimensions, it would be the deficit angle at a like on a triangle. So we would count how many 4 simplices meet at a given triangle. And so the Ricci scalar can be replaced by the sum over the different deficit angles here. And this then gives rise to the so-called Einstein-Regge action. And by performing parts of these sums and using some geometrical identities, one can actually bring it in a very simple and very nice form, which only depends on the total number of 4 simplices on the lattice and the total number of 2 simplices on the lattice. So this is how we can discretize the Einstein-Hilbert action and put it on a lattice. And then the idea again, is to perform Monte Carlo simulations weighted by this Einstein-Regge action. But unfortunately, in d equals to 4, just with this vanilla picture that I've shown you, one didn't find a physical phase, and there's also no indications for a higher order transition in this plane spanned by kappa 2 and kappa 4. Now, one, I think the most prominent direction is to is then CDT, so causal dynamical triangulations, where one imposes a causal structure in the gluing of the triangles or of the tetrahedra. And this gives rise to a rather rich phase structure. And there are indications for indeed 2 different higher order phase transitions where the continuum limit can potentially be taken. I would, or what I focused on in collaboration with Jack Leo and collaborators in Syracuse, was to add a measure term, so-called measure term here, into this partition function. And so this O of Tj is the triangle order, so the number of four simplices that meet at a given triangle. And if you remind how I introduced the curvature, this is exactly how this is exactly related to the deficit angle, and in a sense to curvature on that lattice. So you can think about this measure term as being some combination of higher order curvature operators that then on the lattice have to be tuned in order to hopefully find a continuum limit. And the phase diagram is then typically explored in beta and kappa 2. And the hope is that along this transition line AB, which is a first order transition and which is the transition that is also discovered in the original approach, that when following along this line, there is a critical endpoint where a continuum limit might be taken. And so the idea that I find very intriguing is to actually use matter as a probe to investigate whether this following along the transition and looking for a continuum limit might be realized or not. And for this, in this collaboration with Mingwei Dai, Jack Leo, and Judah Unmut-Yockey, we did that, and we studied scalar fields on these dynamical triangulations in a so-called quenched approximation, where we really throw the scalar fields on the triangulations and like investigate the equations of motions, for example, or what their behavior on that fluctuating spacetime without coupling back the presence of the scalar fields onto the spacetime. So in a sense, we really just look at the properties of a matter propagating on this fluctuating spacetime. And one can do that by discretizing the scalar field on the lattice. So these are just technicalities. And then we extract the binding energy of 2 scalar particles and the renormalized mass from the 1 particle and 2 particle 2-point correlator. So think about it as a propagator. The propagator of a particle depends on the mass. And we can therefore use the propagator to extract the mass. And by comparing the 1 particle propagator to the 2 particle propagator, we can extract the binding energy, because which is just defined as the difference between the mass of the bound state, so of a 2 particle state, compared to 2 times the 1 particle mass. So by comparing the 1 particle and the 2 particle 2-point correlators, we can gain access to the binding energy. And in the continuum and non-relativistic limit, so solving a Schrödinger equation in a gravitational potential, one finds that the binding energy actually depends on on the mass of a single particle to the power of 5. And we can extract this power law from our lattice simulations. So we fit the extracted binding energy as a function of the renormalized mass. And this is shown here in the plot, where alpha is this exponent, and these points here indicate different lattices at different, like, lattice spacings in a sense, and different volumes. And all of these different points give rise to a particular exponent of alpha at that lattice. And then we have to, because we are still on a lattice, so we have to perform the continuum and infinite volume limit. So we have to extrapolate alpha, and the extrapolated value, or the fit, the extrapolated value leads to alpha equals 4.6 plus minus 0.9, which translates, because this exponent actually is dependent on the dimensionality, which translates to d equals 3.9 plus minus 0.2. So in a sense, our simulations, or the simulations that were performed, indicate that indeed a non-relativistic limit that resembles a four-dimensional universe might be possible. So it's consistent, or it might be consistent. And therefore, indeed, Euclidean dynamical triangulations might be one additional method to explore asymptotically safe quantum gravity, but now using lattice methods. And I think I'm a little bit over time, and I apologize for that. So let me just briefly summarize. So asymptotic safety, again, is just the quantum realization of scale invariance. And I've advocated that matter in quantum gravity is very nice and very important, and also very powerful, because it actually provides us with a plethora of phenomenological consistency tests, because we just know a lot of things about matter by observations. And I've also advocated that the gravity-matter interplay might actually go beyond consistency, and we can try to exploit it or to use it to explain some fundamental properties of our universe, for example, the symmetry structures, our dimensionality, or the matter content. But again, everything that I've shown you are just first steps towards answering these questions, and it's very important to try to solidify these kind of results. And then finally, I've tried to argue that there might be some evidence for asymptotic safety from Euclidean dynamical triangulations. And with this, I'm done, and I'm sorry to go over time, and I thank you very much for your attention.
Yes, thank you very much for your very nice presentation. Now we will have, or we will continue with the discussions